Ideal gases. So the first thing we're going to talk about with ideal gases is the ideal gas law. And the equation for the ideal gas law is PV equals nRT. Now, pressure, it says it needs to be in atmospheres. Pressure can also be in one other unit, and that is kPa. Volume must be in liters. N is the number of moles. R is a gas constant. Now, this is where pressure and our gas constant are related. If we have a gas constant, I will say if we have a pressure of atm, we must use this first gas constant to make sure our units cancel out. So we must use 0.08206 liters times atmospheres over moles times Kelvin. If we have a pressure in kPa, we can then use this R value, this gas constant, 8.3145 liters times kPa divided by moles times Kelvin. And our temperature must be in Kelvin. So an example, it says at 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kPa. How many moles of nitrogen gas are in the tennis ball? So we know our equation, PV equals nRT. Pressure, we know, 212 kPa. Our volume is 0.148 liters. We're looking for our number of moles, so N is our variable. Now we come to R. We see we have a pressure in kPa, so we're going to use our second gas constant. We're going to use 8.3145. And then our temperature is 34 degrees Celsius, so we have to add 273.15 to that. And we would get 307.15. So now, 212 times 0.148 is 31.376 equals 8.3145 times 307.15, and we get 2,553.798, so we'll just say 80, and then N. So how are we going to get N by itself? Divide by 2,553.80 on both sides. And we get 0.012 moles of nitrogen gas. Now, last example. This is a deep underground cavern, contains 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.5 times 10 to the 3rd kPa and a temperature of 315 Kelvin. How many kilograms of CH4 does the cavern contain? So, we have PV equals nRT. So now, we know our pressure. It is 1.50 times 10 to the 3rd kPa. Our volume we also know, 2.24 times 10 to the 6th liters. Now, it says how many kilograms of CH4. So that's what we're trying to solve for. And the only variable that could actually correspond with kilograms is N. So we need to find the number of moles first. So our same gas constant as before, Our pressure is in kPa, so we need to use 8.3145 and then multiply that by 315. So 1.5 times 10 to the third times 2.24 times 10 to the sixth and we would get 3.36 times 10 to the ninth equals 8.3145 times 315. It'd be 2,619.07 N. So what do we need to do? We need to divide by 2,619.07 on both sides. So 3.36 times 10 to the ninth divided by 2,619.07. And we would get 1.28 times 10 to the sixth moles of CH4. But we're not done yet. Okay, so now we have 1.28 times 10 to the sixth moles of CH4. And we know CH4, we have 12.01 plus 4.04. So we have 16.05 grams for the molar mass. So we have 16.05 grams of CH4 divided by 1 mole of CH4. Now we want to go to kilograms, so we know in 1 kilogram of CH4 we're going to have 1,000 grams of CH4. So 1.28 times 10 to the sixth times 16.05 divided by 1,000. And we would get, I'll put this right here, 2.05 times 10 to the fourth kilograms of CH4. Okay, so now we go on. We're going to talk about ideal gases and real gases. So an ideal gas is one that follows the gas laws at all conditions of pressure and temperature. Its particles could have no volume. There could be no attraction between particles in the gas. There is no gas for which these assumptions are true. So an ideal gas really does not exist. So at many conditions of temperature and pressure, a real gas behaves very much like an ideal gas. The particles in a real gas have volume. There are attractions between the particles, and because of these attractions, a gas can't condense or even solidify when it is compressed or cooled. And we know that. And this graph shows how real gases deviate from the ideal gas law. And you'll be doing an activity with this later in the week. with this chart. So this will conclude our video on ideal gases.